You thought the roast was over?
All right.
Part two.
Come back. Beginning.
The position of a particle is given by the following equation. So the particle is taking on what type of motion? What type of equation is this? Quadratic. If we have a quadratic, what do we automatically know about acceleration? It's a constant. So like that's something just to keep like in the back of your mind when you see your formulas. If you have a quadratic position, you have a constant acceleration right off the bat. You could. Movement can also be a trig function. You can also describe movement as like a cosine or sine.
That is quantum something, but is there anything that
Bees, the movement of bees, the wiggles and waggle movements, like that can be a function too.
What?
That's how bees move. I'm not making that up.
They wiggle and waggle.
I would like to see a fact check.
Okay, I'll prove you.
Yes,
I'll prove it
we
again.
wiggle and waggle.
So we walk and run, and they wiggle and waggle.
Their wings still get
I shot
All right.
his wings off with a pellet.
So never brought that up. S of t equals t squared minus 4t plus 3, where t is measured in seconds and s is measured in meters. Find the displacement, so again, displacement, of the particle during the first 2 seconds. So displacement is final minus initial. It's just like where you end and where you started. You don't have to worry about all the points in between. That is distance. So what we need to know is initial. So we need to know what is S of 0. So its initial or starting position is 3. We want to know displacement after 2 seconds. So we need to know what? Good. So S, you get 2 squared minus 4 times 2 plus 3. So we get 4 minus 8 plus 3. Get negative 1. So displacement is final minus initial. So in the case of this problem, it'd be S of 2 minus S of 0. Yes, or you could refer to it as the change in S or delta S. So S of 2 we said was negative 1. S of 0 was 3. Therefore, the change in position is negative 4. So we were given units, right? So it's negative 4 meters. What does that mean in terms of a graph or in terms of position? The particle is what? Yeah, 4 units either to the left or it moves 4 units backwards. So okay. Part B, find the velocity at time t. So you are just finding the derivative of position. So go ahead and find the derivative of position. And put the units after it.
Wait, is this for B?
Yes. For part B, find the derivative of position and list the units after.
Wait. I did JKIL. I think I don't know my previous JKLMN.
You're 100% correct right now. Other than the fact that you're like 4 problems in a row.
You're on like the wrong page. Again.
Okay,
He's on the right page.
So why is he on JKIL?
Because
Because
we don't have, we start on.
Oh, because it kept the numbering from the previous page.
Yeah.
Okay. I was like, what?
So you can really
Yes.
smooth right now.
So here's the second part. Find the velocity at time t. So you got 2t minus 4 meters per second.
Wait.
Oh,
I mean, it's
Oh.
the life.
Never mind.
you can't really help it.
Okay, if it asks for the velocity after 3 seconds and after 4 seconds, what are we doing? Plugging in. That is instantaneous velocity. If it does not ask for average, you are assuming instantaneous. Instantaneous is plugging into the derivative. So in part C, we are finding V of 3 and V of 4. These are our instantaneous. I even put like a little note. Average velocity at 4 seconds would be different. Average velocity at 4 seconds would be s of 4 minus s of 0 all over 4 minus 0. Do you see how average velocity comes from the position, not velocity functions? It is the slope of position. Okay, go ahead and derive velocity to find acceleration. And we already discussed acceleration is going to be a constant. So if you do not get a whole number, you'll derive incorrectly. Our units are meters per second squared. That means the acceleration at any point is always 2. Does not matter where you're looking. The next question is, when is the particle at rest? When would the particle be at rest? How would we go about finding that? Perfect. So standing still and at rest are like the same thing. Velocity is 0. There is no movement. If velocity is 0, we're not moving. So go ahead and set your velocity equal to 0 and solve for time t. So again, a lot of what we're doing in these problems is kind of like going back to algebra. We're solving for variables. We're looking at quadratics. We're looking at functions. So when the velocity is 0, we have 0 equals 2t minus 4. Solving for t, we get t equals 2 seconds. So if the velocity is at rest, if the particle is at rest or not moving at 2 seconds, what we want to do is investigate, does the particle change position, direction? So is it going forward and then going backwards? Is it going backwards and then going forwards? So we want to know what is happening directionally around 2 seconds. So we're going to come up with a velocity position number line. Now, number lines are useful and helpful. However, on AP tests, they will not look at them or grade them. So they are for you to create information and details, but you have to be able to put it into words or put it into interval notation. So Here's our function. We have 0 seconds. 1, 2, 3, 4. So what we want to know about the particle is what is happening. We know that v of t equals 0 at t equals 2. So what that means is we want to know what is the velocity to the left of 2. So what's the velocity at 1? Let's plug 1 into velocity. 2 times 1 is 2. 2 minus 4 is negative 2. So the velocity from 0 to 2 is negative. How about bigger than 2? Positive, right? We plugged in 3 and we plugged in 4. When we plugged in 3 and 4, we got positive numbers. So the velocity is negative or less than 0 from 0 to 2. Velocity is positive or greater than 0 from 2 to wherever the particle stops moving. At this point, we don't have an end, so we'll say infinity. What does that mean then in terms of direction? If velocity is negative, the particle is moving in what direction? Left. So, from 0 to 2, so left from 0 to 2, right from 2 to infinity. Does that answer the question they asked? Yeah. Remember, we can include 0 but not the 2's, because at 2, the particle has no velocity, it is 0. Okay? Graph position, velocity, and acceleration on that number line. If anybody wants different, I would colored pencils and crayons if you want them. Let's start with position. So we said that the particle started at what point? What was S of 0? 3. So we know S of 0 is at 3. Okay? Then we said that at S of 2 we were where? Okay? So at 2 we're at negative 1. And did we find any other initials? I kind of had it on the average velocity slide, right? At S of 4 we are at 3.
Alyssa White, Kaylee Pitcock, and Jimmy Sadler, please report to the office.
Again, I know it's a quadratic.
Also, Alyssa Doherty, please report to the office.
Here we go. That's my name. So these are actually zeros. If I plotted perfectly. Because a quadratic is up 1, right 1, and up 4, right 2. I got it. Okay, go ahead and graph your velocity and acceleration. You're welcome. Okay, so for velocity, we had some key points on velocity too. We said v of 3 was 2. We said v of 4 was 4. Oh, I plotted 3. I was like, what? Thank you. It's up 2. Yeah. That's why I was like, what can't I can't look at my board and do this. Remember, we have a starting value at 0, but this had no ending point. So these have to have arrows that imply it continues forever. Acceleration was a constant at 2. So acceleration is just going to be a horizontal line at 2. If acceleration is always 2, acceleration is always positive. Go back to our chart from way back when and think about what a positive second derivative tells you. Tells you the original is always what?
Concave up.
Can we not see how my quadratic is always concave up? So again, those things, those ideas come from this aspect. So, the last thing we didn't talk about is speeding up and slowing down. I want to talk about speeding up and slowing down in terms of this problem. I know it's not on there, but this is an easy problem to see it. In order for an object to be speeding up, 2 things have to occur. Either both velocity and acceleration are positive, or velocity and acceleration are negative. So in order to be speeding up, the signs of the derivatives have to be the same. So for speeding up, so that means they're either both positive or both negative. Slowing down will be opposites. So an object is slowing down when velocity and acceleration have opposite signs. And it doesn't matter who is who. So, looking at this graph, acceleration is always positive. Velocity has negative and positive aspects. It changes sign right here at time t equals 2. So from 0 to 2, acceleration is positive, velocity is negative, therefore the particle is perfect. So it's slowing down from 0 to 2. From 2 to infinity, velocity is positive and acceleration is positive. Therefore, the particle is speeding up from 2 to infinity. Not exponentially, just speeding up. For those of my non-physics kids, are position, velocity, and acceleration starting to click a little more? Are we creating that better connection?
then we'll find out if you're at a 50 or
Okay. So what I want to do now is go backwards in your note one page. Yes. Example 2. So what you're going to do is, and if you need a pencil, I have pencils. I want you to try part A, which is velocity, part B, which is velocity of position, and part C on your own. So take like 4 to 5 minutes and do A, B, and C now just to start, and then we're going to talk again before you move forward just to make sure we have A, B, and C correct. Pencil. Oh, are you missing one? There you go. Yeah, there's extra pockets. Sorry. Correct. All right. Everybody good to check ABC?
1 second, please.
Okay. Okay. So velocity, power rule says 3t squared minus 12t plus 9. Good. Velocity at 2 says everywhere you have that t, so you get 2 squared minus 12 times 2 plus 9. So we get negative 3 meters per second. V of 4. Positive 9 meters per second. Okay, when is it at rest? Well, it's at rest when 3t squared minus 12t plus 9 equals 0. If I were doing this problem, I would factor out a 3 to make this easier. So I would take out the 3 and I would leave myself with t squared minus 4t plus 3. So then when you factor it, you get 3t minus 3, t minus 1. So the times at which the particle is at rest is t equals 3 and t equals 1.
It's already shattered.
It's funny how
You have nothing else to lose. Yeah, like, I really.
there's a good thing about it.
Is that worse?
It's not any worse.
There we go. Not any worse.
Well, these can't get any worse.
Don't do it.
Clay's battery.
Clay just chucks it across.
Buddy,
All right.
you should stab that battery with
Go ahead. Take a minute if you have not already done so. And take into account part D, which says when is it moving forward? And honestly, if we're doing forward, we can easily do backwards. And remember, typically these flow into each other. So why do you find it at rest? Well, at rest gives you the idea of finding it moving forward or backward. So when you're looking at these, part D, or part D, this is where I would almost look at that number line again, and I'd say, okay, here's what I know. We start at 0, and I know that the particle is going to change directions at 1 and 3 possibly. Not for sure, but possibly. I already know the velocity at 2 and the velocity at 4. At 2, velocity is -3. So from 1 to 3, velocity is negative. It cannot change signs unless the particle goes to rest. So if I know at 2 it's negative from 1 to 3. Does that make sense? Cool. We know at 4, velocity is positive. So that tells me velocity is positive from 3 and up. What don't I know that I need to know then? 0 to 1. So you gotta plug in like a half. I don't care what the number is, I just care what the sign is. So a half cubed is gonna be a pretty small number, like 1/8. Okay? So 1/2. So we need to find v of a half. So you get 1/2 squared times 3 minus 12 times 1/2 plus 9. So 1/2 squared is 1/4. So you get 3/4 minus 1/2 times 12. So -6 and 9 give you 3 plus a 3/4, so it's positive. Yes. You never want to look at the initial or like the starting value, just in case. We never like really look at 0. But I get what you're saying. You saw it was 9, so you kind of knew it was positive.
If 0 solves for one of your zeros, you wouldn't be able to.
Yeah, and that will happen. We'll have zeros that are zeros, but not on position, velocity, and acceleration because they're objects.
Isn't finding 0 the initial velocity? Wouldn't that tell you what it is? If the initial velocity is positive, then you know it's positive until it changes.
Yeah. So I said, I was like, I always hesitate to put in and look at 0. Right. So if it's positive 0 to 1 and 3 to infinity, then it is moving forward. Backward. 1 to 3. If you don't like this notation, you could also do interval notation. So like if you don't like the set, like that is acceptable too. So 2 notations, same thing, mean the same. Totally can trade back and forth. Okay, letter E. E is now talking about acceleration. So the acceleration will be 6t minus 12. Part F, what is the acceleration at 4? Units will be meters per second squared. Let's graph this. Okay. So, let's start with position. What do you know about S of 0? No. 0. Because I love a T.
Oh, 9 T does have it, right?
So, starts at 0. What do we know about V of 0? It will be 9. I'm going to go by 3s. Can you fit all yours? I gave you, no. Go by 2.
I just went way off.
Yeah, I just made my own graph.
You look too long. I mean, with the acceleration,
I
well,
literally
that
just
comes pretty far off the
extended
graph
it.
either way.
But the velocity graph in the,
I'll make it with 3s, won't I? I'll make it with 3s.
You'll be okay with 3.
Yeah.
I just did by 1s and it was nowhere near close to the graph.
Okay, and then acceleration starts at negative 12. Yes. 16 minus 12. Did I do it wrong? Okay. I was like, what? Okay. So again, I went by 3s just to try to help me out. So those are all my initial and starting points for the 3 graphs. So again, I did A in orange, velocity in red, position in blue. Okay? We know velocity at 2 and 4, so those are easy points to graph. So V of 2 is negative 3, and V of 4 is positive 9. the zeros of velocity are going to occur at 1 and 3, which we also found out in part C. So I know my zeros and I know my heights. What do you know about the zero velocity? What does that have to be on the original? Velocity is a 0. On the original, it is an extrema. So that means the position function is at a maximum or a minimum at 1. So let's find S of 1 so we have a little bit more of an accurate graph. So 1 minus 6 is negative 5. Negative 5 plus 9, 4. So at S of 1, we're at 4. That means at S of 2, my graph better be lower than that one. Think about t cubed minus 6t squared plus 9t. You could take out the t. That's how you get your starting 0. Then you have t squared minus 6t plus 9. Is that easily factorable? So what does that mean happens at t equals 3? Does that mean then that this point here is also an extrema? Perfect. So that gives us a rough idea of our graph. Okay, connect your velocity graph. Remember, these go by 3s, so an acceleration of up 6 and over 1 would go up 2 on y and over 1. Can we see here almost the point of inflection occurring on the blue graph? We see at the 0 of acceleration, the POI on the blue graph, concave down to concave up. Okay, here's the biggies. Find the total distance traveled by the particle during the first 5 seconds. Find the total distance. So, to find total distance, you have to take into consideration what? What?
Delta S.
Okay, delta S, and you have to take into consideration when the particle changes direction. Perfect. So we're looking at the position from the interval 0 to 1. We're looking at it from 1 to 3, and 3 and on. But it only says during the first 5 seconds, so it's 3 to 5. You what? Yeah. Down there. Okay, so we need to find the position of the particle at S of 0, S of 1, S of 3, and S of 5. We found a lot of them on the previous parts graphing. S of 0 we said was, S of 1 we said was, S of 3 we do not know. And S, do we know it? Oh, it's S of 3, 0. We don't know S of 5, sorry. I got ahead of myself. S of 5 we have to plug in. Alright, over to you.
I needed to graph and make sure all my points.
I'm just giving you a hard time. So what we need to do now, though, is find the absolute values of all these changes. So it's the absolute value of S of 1 minus S of 0 plus the absolute value of S of 3 minus S of 1 plus the absolute value of S of 5 minus S of 3.
1, 1, 3, 3, 5.
Okay. Yes.
Does it matter if you do S of 0 minus S of 1 or S of 1 minus S of 3? Because I did all of mine like backwards.
It shouldn't matter because it's absolute value.
Okay.
So here, 1 minus 0, absolute value is 4. 3 minus 1 is negative 4, but absolute value makes it 4. 5 minus 3 is 20, absolute value makes it 20. So you get 28 meters. Who said seconds? Hey,
I think you should automatically be
I.
wrong
Well, why
because
is
you
it a
said
plus
that.
sign?
No.
Yeah, I definitely agree with that one, though.
Wait.
Who did it?
No, it has something to do with like the recording thing. Look, there's like this weird bar here.
Oh, ew.
It's
Like
recording what
erase?
you
I
write.
don't know. Okay.
Like erase.
So this is goofy. It slows down when velocity and acceleration are opposites in signs.
I'm so
It's gonna
smart.
give me a stroke, man.
I know.
I'm sorry, I don't know how to fix it. So
Maybe
damn,
try,
like even go back.
try
Yeah, because
pressing
you wrote over top of it.
Sure, let's try that. Oh, that was weird. All right, so when it is slowing down, the signs of velocity and acceleration are positive. Acceleration is negative from 0 to 2. Velocity is positive from 0 to 1. So therefore, the signs are opposite from 0 to 1. So therefore, the function slows down from 0 to 1. Acceleration becomes positive from 2 on. However, velocity is still negative from 2 to 3. Therefore, these are on opposite sides of the x-axis. Therefore, it's slowing down from 2 to 3. Speeding up are when they are on the same side. So that's from 1 to 2 and 3 to infinity. So again, you can see that graphically. From 1 to 2, both are down here. From 3 and on, both are above.